Okay, dear friends. So we have one more section in the first unit to cover. So that is regarding connected sets. You know what is meant by connectedness. So connectedness is defined in terms of paths, arcs connecting. Okay, connecting any two points if there is an arc or path. Okay, like that. So we define connectedness of sets in a different way. So that is by defining separated sets. Okay. So what is a separate? What we mean by sets are separate. So we have two sets A and B are said to be separated if they satisfy this relation: A intersection B closure is empty and A closure intersection B is empty. That means the closure of B does not contain any point from A and closure of A does not contain any point from B, or A does not contain any point of B or any limit point of B, and similarly B does not contain any point of A or any limit point of A. So such sets are called separated sets. For example, we have the segments 0, 1 and 1, 2. So if this is A and this is B, we have A closure is closed interval 0, 1. B closure is closed interval 1, 2. You can see that A closure intersection B. We have the B is segment 1, 2 and A closure is 0, 1, interval 0, 1. So they don't have any common element. So it's empty. And A intersection B closure, these two sets, in segment 0, 1 and interval 1, 2, they do not meet. Okay, again, so that these two segments are separate. Of course, the segment AB and CD are separated, provided AB less than B less than C less than D. So if they satisfy this relation also, they are separated, okay, for any two intervals. Now we can define what is a connected set. So the connectedness of sets is defined by using separated sets. A definition of separated. Okay. So the definition is this: a subset A of a metric space X is said to be connected if there does not exist two subsets for example, you can consider instead of A which is like E is said to be connected if there does not exist two subsets A and B. To just follow the definition, the notation of the definition. Notations used in the definition. So subsets A and B, there does not exist two subsets A and B of E such that A is equal to E is equal to E union B, A union B, and A and B are separate. So if there does not exist, so these are the two conditions. Subsets A and B of E such that E is the union of A and B and A and B are separated. In other words, a set is connected if it is not the union of any two separated sets. Okay? If it cannot be written as a union of two separated sets. For example, the sets 0, interval 0, 1 or segment 0, 1 because if you take any partition of 0, 1 interval or segment, so if you partition this set into two sets A and B, it cannot satisfy separate ones. Okay, but it cannot satisfy A closure intersection B is empty and B closure intersection A is empty. Okay, if you cannot write 0, 1 as a union of two sets A union B satisfying the property A closure intersection empty, A closure intersection B is empty and A intersection B closure is empty. Similarly for 0, 1, this is not possible. Okay, so they are connected sets, and we will see that we have only theorem in that section is the connected subsets of R are precisely the intervals. Intervals means maybe open interval, that is segment, or closed interval, maybe semi-open intervals, maybe unbounded intervals, semi-open rays, they are called rays, maybe unbounded as well. So the only connected subsets of R are intervals. Okay, that is ensured by the next theorem. So this is theorem. This is regarding connected set in R only. So a subset E of R is connected if and only it satisfies the full. What is if X and Y are elements of E and X extend Z extend Y, then Z is an element of intermediate value. So given any 2 points in the set E and any point in between that two must be in the set. So that will be a characterization for connected sets in R. So if any subset of R satisfying this condition, it is connected, and if a subset of R is connected, then it must satisfy. That means every intermediate points belong to the set. Intermediate points of any 2 points of the set. So that is why we get the connected sets are intervals. Okay, corresponding to every 2 points, all the points in between that two is again in the set. So we get all the line segments in between any 2 points in the set. So we get the entire interval, some interval as a connected set. Okay. Anyway, how to prove it? So we are proving one by one the negation. You know, in order to prove P implies Q, it is enough to prove minus Q implies minus P. Okay, to get P implies Q, it is enough to prove minus Q implies minus P, the negation of the statements. That's what we are going to do here. So here suppose in order to prove the implies part, that is if E is a connected subset of R, then E satisfies this one. Okay, we want to prove this. So we assume E does not satisfy this, then we want to prove that E is not connected. Okay, so in order to prove P, if this statement E is a connected subset of R, E is taken as the statement P, and this statement is taken as the statement Q, then to prove P implies Q, it is equivalent to prove Q minus Q implies minus Q. So what we are going to do. Okay, so we assume E does not satisfy Q. Okay, let E be a subset of R which does not satisfy Q. That means what? There are 2 points, that is, there exists 2 points x, y in E, and there is some point Z in xy, that is x less than z less than y, such that z is not equal. So the statement Q is not satisfied means Q says that whenever x and y are points in E and z is a point in between x and y, then z must be equal. So that is not satisfied means there are some points x, y, z in R such that x and y are elements of E, x less than y, z is in between x and y, and z is not an element of, but z is not an element of E. So, okay, that is the negation of the statement. If Q is not satisfied, this is true. Okay, so some z is there, satisfied. So we want to get P also cannot hold. Okay, we want to prove that P also is not. That means we want to prove that P is not true. That means the set E is not connected. P is not true means the set E is not connected. So here we prove E is not connected. So how to prove E is not connected? So that approach is more easy than to prove a set is connected. Okay, to prove a set is not connected, it is enough if we find two subsets A and B which are separated and their union is the set. Okay, so that is more easy. So anyway, so how to get two subsets? So here we have some subset E of R. We have to divide this subset into two sets A and B in such a way that they are separated and their union is E. Okay, so we are using this fact. We have already selected an element, some elements x and y in E, and an element z is not in E but lies in between x and y. So we use this element to divide the set E into two. Okay, so how we can do is this. So z is an element of R. Somewhere z is there, x is somewhere less than, and y is above z. Okay, we have the points like that. So what we are doing is we divide the E into two sets. Those are less than, those points in E which are less than z, and those points of E which are greater than z. Okay, so we define the sets if is the points in E which are less than z. That is exactly E intersection minus infinity because it is in R. Okay. And similarly, we define B is the set of points in E which lies above Z. That means it is E intersection Z plus infinity. This is the, of course, as Z is excluded here from these two segments, Z is excluded, but Z is not a point of E, so this union will constitute A. So this will imply not A, B. Union of A and B will be the set E. Of course, union of A and B is E. Now we prove that E is separated and A and B are separated sets. E is the union of two non-empty separated sets. Okay,